Day 162, Honors Physics, Photoelectric Effect, problem number 20. I guess this is really an energy problem, not really photoelectric effect. Quantum physics. Anyway, we once again have the power equation. Power is energy over time, so this is where I started the problem. You could have started over here on the right, but I started here with power is energy over time. The power of this laser beam is 1 milliwatt. It's 1 times 10 to the negative third joules per second. Equals the total amount of energy, and it says we're using 1 second as our time. How many photons per second? So they told me it's 1 second's worth of time. So therefore my total energy emitted by this beam from this laser is 1 millijoule, 1 times 10 to the negative third joules of energy total. So back over here on the right, I'm calculating the total energy of, the energy of one photon. So I use V equals lambda F. And as you know from previous problems yesterday, you could take a shortcut here by combining these two equations, but I'm not doing that right now. V equals lambda F, I have the frequency of these photons, the individual photons. Then the energy of an individual photon here will come out if I'm using the joule version, which I would like to do because my power was in joules per second. The energy of my photons will come out here. So once again, you're going to plug this in for F, and then the energy will come out in joules, and then you will take and divide this number, the total amount of energy, by the individual energy of each photon to see how many photons it takes to make this much energy, because this is the big number. How many little photons does it take to make this relatively large amount of energy compared to the actual photon itself? I would like to say as well, I mean, this is not a lot of energy really, but all I'm saying here is that this energy is a lot more than this. In the scope of life, this really isn't that much energy.